Right, let's get to the starting video on the waves. This is the first video on many videos coming on the waves. Waves is a big topic in A-level physics. I'm starting today from the concepts that you did in GCSE and building on that. So the first thing that I want to talk about is the word progressive wave. So the word progressive wave is used to describe a wave that is traveling, because now you'll also be learning about the waves that are not traveling, that is stationary waves. So let's just get started. So I'm going to make up. So this is a general model of a wave. So whenever you'll see anyone talking about waves, whether a question or anything, they'll model a wave like this. Why is it a progressive wave? Because it progresses from point A to point B. And what it is defined as, it is a disturbance that is continuous disturbance, which transfers energy. So in the diagram that I have made, our energy is traveling from A to B. Now, every wave has a characteristic, and those characteristics are defined as, first, the amplitude. So amplitude is the maximum possible displacement from a starting position. So that would be your amplitude. Okay. The distance between two troughs, the bottom, this is the anatomy of a wave. The bottom parts are called troughs. This is called crust. So any 2 points which are like at the same position. This year you'll also be learning about something called as phase, but that later. So right now, consider this. Any 2 points which look like at the similar position, those 2 points are always separated by wavelength. So this lambda here is wavelength. So wavelength is the shortest distance between any 2 points which are in similar positions. For example, consider this particle here. Now, exactly similar particle is this one. Even this is similar. So the distance between this point, let me just take another color. So if I take point, this distance is wavelength, and this distance is also wavelength. So shortest distance between the 2 points which are in similar position, and then they are also called as in phase, but the meaning of phase a little later. Then we define frequency is the number of disturbances produced every second, and it is measured in hertz. So how many waves, how many disturbances are produced every second, that is a frequency. And then we also define time period. It's the time taken for one cycle of a wave, okay, and it's defined as 1 over frequency. And clearly the unit would be seconds because it's nothing but the time period. Okay, so this is the basics of the waves that you've done already in GCSE. If you want to brush up, go to the GCSE video on waves and try to brush it up. If you're okay with that, let's get moving. Now, any kind of wave, so generally what we do is we define all the waves into 2 categories. One is mechanical. Mechanical waves are the waves that require medium to travel. They cannot travel in vacuum. Like sound waves. Sound waves are mechanical waves because they cannot travel in vacuum. And then you have non-mechanical waves which do not require medium. They don't want any medium to travel. They can also travel in vacuum. For example, electromagnetic wave, light wave, the common word. Okay, it is electromagnetic wave. Some of the examples don't accept the word light because all parts of electromagnetic waves are not visible to our eyesight. So we say electromagnetic waves. So all the waves are divided into two major categories. Actually, there's a third category also, but we are not talking about that. A level physics, mechanical and non-mechanical. Mechanical waves are the ones that need medium. Now, mechanical waves are further categorized as longitudinal. You've done that in your GCSE again, but I'll be just going through it. And the second one is transverse. Now, what are they? Okay, now as you can see in the small animation, the left one is the longitudinal. So my energy is traveling in this direction. So this is the travel of energy. But if I see any small particle here, one particle, let me just change another color here, right? So if I choose this particle here, so see how does this particle moves? This particle moves in this direction. So the oscillations are parallel to the energy transfer. That's your longitudinal wave. Oscillations or vibrations. So why vibrations? Because the particle does not shift, it just moves forward and comes back. So any forward or backward motion is oscillation. So as you can see, this particle has not gone anywhere, it just moved forward and then came back. So oscillations or vibrations are parallel to the energy transfer. Whereas in the transverse wave, if you see this particle here, it just goes up and down. So this, now energy transfer is still in this direction. So this is the energy transfer, whereas the particle movement is, or oscillations are perpendicular to energy transfer. So the angle is 90 degree. So that's your transverse. So transverse oscillations are perpendicular to the energy transfer, whereas longitudinal, they are parallel to energy transfer. This is an example of non-mechanical wave, the one which is colored. It is your electromagnetic wave. Now, electromagnetic wave comes from electric and magnetic field. So as you can see, on this line, the blue color is the magnetic field, and the red oscillations are the oscillations of electric field. So E electric field is perpendicular to magnetic field. So, and both the oscillations, they are perpendicular to the direction of energy transfer. Energy transfer is happening in the x-axis. So this is the direction of the wave, so x-axis. And electric field is the y-axis, perpendicular, and magnetic field is along the z-axis, again perpendicular. It's difficult to make this in 2 dimension, but I'm just going to shoot this as my z. So oscillations are perpendicular to the direction of wave. That means what kind of wave is this? This is a transverse wave. So non-mechanical wave, electromagnetic wave, is transverse in nature. It is not longitudinal. And also, just because we are saying that electromagnetic wave is transverse, we're not saying it is proven. And we, at the same time, let's just say, tell you what is the nature of the sound waves. The sound wave is longitudinal. So sound waves are longitudinal and mechanical, and electromagnetic waves are non-mechanical and transverse. Now, every single type of wave, what kind of behaviors do every single kind of wave shows, whether it is transverse, longitudinal, mechanical, non-mechanical. So some of the key behaviors is, one of the behavior is reflection. Every wave can show this phenomena. Reflection is bouncing back from a surface. Okay, that is reflection. Second is refraction. Refraction is when a wave enters another medium. So this is medium 1 and medium 2. So whenever the medium changes, the path of the wave changes. So as you can see, there's a little bit bend, so that is a refraction. Then you have phenomena like polarization. Now these are the new phenomena, new behaviors, and you'll be learning more about them. They are the part of your A-level physics. So polarization is when you restrict the oscillations in one direction or one plane, but this happens only with transverse waves a little later. So this is later. Then you have phenomena like scattering. Okay, the waves, sound waves or electromagnetic waves, any kind of wave can scatter whenever it faces proper conditions. So again, later. Then you have phenomena like superposition. Okay, superposition is when two or more waves overlap. Okay, this is a major part of your waves topic, superposition, learning about superposition and types of superposition, what different phenomena superposition can produce. This overlapping of waves sounds so simple, can produce different kind of phenomena, interference, stationary wave, but so there are different behaviors all kind of waves can exhibit. Now this could be your 2 marks or 3 mark question. What is the similarity between a non-mechanical wave and a mechanical wave? They both show reflection, both shows refraction. What we are focusing today is on refraction. But before that, a new word, wavefronts. Now wavefronts, what is a wavefront? It is a line or an imaginary line joining all the points on a so it's a line joining all the points on a wave that are in same phase. Okay, now to be able to understand that, let's understand the meaning of phase. So phase just means the particles would go to their maximum at the same time and would go to their minimum at the same time. So if I have three particles, let's say, they all become maximum, they go up at the same time, and then they come back, they go down at the same time. So if they are in same phase, they become maximum, minimum, their velocity, everything is same. So line joining all those points on a wave that are in same phase, that's wavefronts. So if I'm drawing light rays like this is when you draw a light any wave like lines, then you're doing a ray model. You're drawing rays. Now every single point on these rays is said to be in the same phase. So instead of drawing a ray model, if I show you a wave traveling like this, so what I'm drawing wave fronts. So these are wave fronts. So every point on these wave fronts will be a particle if it is a mechanical wave, and all those particles will be in same phase. So particle A, B, C, D, E, they are all in same phase. Now what's the meaning of same phase? They are at same position and they have same velocity. Now see, this is what I mean. So all these lines, I'm just drawing a line here. So let's just say this line. So all these lines that you can see, the particles on these lines, they are in same phase. So these are all in same phase. So now this is one way to show refraction. Another way to show refraction is by drawing a ray model, because some of the times your exams would have. So this is a boundary that is separating medium 1 and medium 2. Okay, in this case, this is the boundary. So this one is the boundary here. So now what you see on the screen in the form of animation is a wavefront model. I could also show you the ray model. So this is, let's say, if I'm drawing a wave is happening, like entering into the second medium like this, and then because of the refraction, it bends. So that's the refraction. So bending of wave, why does it bend? What's the reason of bending? Because of change in medium. Okay, that's your refraction. Now, why? What's the reason? Why, whenever the medium changes, the wave bends? It is just because the speed changes. So whatever is the speed here, let's say if I say that this is air and the speed of wave is c. So c is a symbol for speed of EM wave in air or vacuum, and the value is, yeah, some of you already know that. I'm still writing it here. C is 3 times 10 to the power 8 meters per second, approximations of around this. So now, and here the speed is v. So the speed has changed, but what does not change? So in refraction, speed of the wave changes. And as you can see, the distance between the wave fronts has decreased as it enters the second medium. So because the distance changes, that means the distance between these two lines is called wavelength. So wavelength changes. But what remains same is the number of wave fronts. Whatever number of wave fronts you have in medium 1, it would be same as in medium 2. So what remains same is the frequency. So frequency does not change, frequency remains same. So if I am teaching you right now, and I'm teaching you very much in air, if somehow I can teach this video, I can make this video in water, the frequency of my sound wave would still remain same. What would change is the wavelength and the speed of my wave. Okay. Now, refractive index is a term that is used to measure how much the speed has changed. So denoted by small letter n. So it is defined as speed of wave in medium divided by speed of wave in air. Okay, so we can write this as V over, oops, I think I've written, okay, this is air and then medium. Because in medium, the speed is always less than the speed in the medium. So I can write V as C over N. Okay, so always the speed of any wave would be highest in air or vacuum. As you put it, if you allow it to pass through any medium, air or a glass or water, its speed is going to reduce. Its wavelength is going to change. You can decide how much is the wavelength changing using, if you remember from GCSE, we have this equation, V equals to F lambda. Okay, so if the speed decreases and frequency does not change, so lambda also decreases. They come closer, wavefronts come closer. Now, n is nothing, it's a refractive index. Now, because it's a ratio of two speeds, it has no unit. Okay, it is just a property of the medium. It kind of tells you how optically dense a given medium is. Snell's law. Now, this one takes care of n, refractive index, and angles of reflection and refraction. Let's just make, now what I'm doing is I'm making a ray model of refraction, okay, because that's the most common one. So first thing you need to do is draw the boundary. So this is my boundary. and let's say a light ray is incident on the boundary. Now what you need to draw is a normal. So this angle here is the angle of incidence. So medium 1, refractive index is n1. Okay, now as it goes into the second medium, medium 2, refractive index n2, if n2 is greater than n1, that is, this is going into a denser medium, it's entering into a denser medium, so refractive index is higher, it bends towards the normal. So this was the original path. It would have gone straight if the medium would not have changed. Now because it has changed, it refracts towards the, so this angle here is angle of refraction, bends towards the normal, so angle of refraction. Now what Snell's law says is that n1 sine I is equal to n2 sine r. Or what I'm just saying is, not I'm saying, Snell's law says that n sine theta is constant. So when you apply on the boundary, n for the first medium is n1 and theta for the first medium is I. N for the second medium is n2 and theta for the second medium is r. So n1 sine I is equals to n2 sine r, or n sine theta is constant. Okay, let's just make this diagram again if your n2 is less dense. So just making here, again the thing I need to draw is a normal. So we've got the normal. My light ray is now incident. Angle of incidence is I. So if there is no change of medium, this is how my light ray would have gone without change in the path. Now because it is going from n1 to n2, and I'm assuming n2 is less than n1. So what would happen is it'll bend away from the normal. So can you see my angle of refraction now is higher than I? But still this equation is valid because this is Snell's law. It does not matter n1 is higher or n2 is higher. n1 sine I will always be n2 sine r. Okay, let's do one simple question. Go ahead, pause and try to answer. Enters a denser medium, so second medium is greater than the first medium. Refractive index of second medium is greater than that of first. Frequency never changes, it depends on the source. Remember, I am making this video in air or in water. Frequency would not change. My voice would remain my voice. My frequency means the kind of voice you're hearing. Wavelength, what would happen to wavelength? Now because you're entering a denser medium, speed decreases, and because speed is equals to f lambda, so because speed is decreasing, lambda decreases. So I can just write decreases. Okay. All right, let's try another one. Light travels from air into glass. So now refracting index for air is 1. Now, and the glass refractive index is 1.5. Please pause and do it yourself. But if you've done that, angle of incidence is 30. They want angle of refraction. So just using n1 sine I equals n2 sine r. Same refractive index, same angle. Don't confuse, don't take n1 and r together. Say, that's why I've written them in same line so that there's no confusion. So now 1 sine 30 is equals to 1.5 sine r. Using calculator to solve, almost 19.5 degrees. So r is 19.5 degrees. Let's do the next one. Now, critical angle. Now, to define critical angle, there are some assumptions, okay, some conditions. First condition is that the light ray should enter a less dense medium. Okay, if it is entering a denser medium, critical angle is not defined. Okay, now what is critical angle? Let's just see. So what I'm doing is I'm making a boundary first. I'm considering this as air and this is water. Now, what's the condition? Light ray should enter from air to water or water to from air. Sorry, from water to air or from air to water. It should go from water to air. Say, I am just considering then. Just want to make it a straight line. We would want our diagrams to look beautiful. Okay, let's try and make a straight line now. Okay, this is better. So now light ray is going from water into air. So first thing I'm doing is I'm making a normal. Okay, otherwise how would I decide what's my angle of incidence? Now this is my light ray. Oops. Okay, you can always try to forward it if you're getting. So this is the light ray angle of incidence. Now, as it is entering a less dense medium, it's going to bend away from the normal. So that's my light ray after refraction. So what happens is, if I increase my angle of incidence, okay, let's say my angle of incidence is further increased. So my angle of refraction would also increase. But if I further increase my angle of incidence at one particular angle, so let's say at this angle of incidence, my angle of refraction becomes 90 degree. Then that angle of incidence is called critical angle. So the angle of incidence for which angle of refraction becomes 90 degree is called critical angle. Now, generally, in this case, my second medium is air. It can be anything. So that's why I'm writing N2 here. And N1 can be water or glass. So if I apply my Snell's law, N1 sine I equals N2 sine R. So when my I is critical angle, my R is 90. That's the condition. So what is critical angle? It is that angle of incidence for which angle of reflection becomes 90 degree. So my N1 is then, if I want to find N1, I know critical angle, I can just write sine 90 is 1. So I can write N2 over sine C. But if I want to find critical angle, which is generally the case, so if I want to find the critical angle, it is nothing but N2 over N1. So in this case, my N2 is 1, so I can just take 1 over N1. Definition, that angle of incidence for which angle of refraction becomes 90. Okay, let's go ahead and try and do this question by pausing. I'm going to do this. Critical angle for a glass air boundary. So it's going from glass to air. So my N2 is 1. N1 we don't know. Critical angle is given as 42 degrees. So I'm just using sine C as N2 over N1 sine 42. This is 1. We want N1. So N1 is 1 over sine 42. Using my calculator. Answer is approximately 1.49. this is 1.49. What's the condition? Condition is, you remember that it has to travel from dense to less dense. So my first medium would be glass and second would be air. Always for a critical angle. Otherwise, it is not defined. The critical angle is not defined. Okay, go ahead, pause and do this one. Light and water, N is strikes the boundary with air. So it's going from water to air. So it's going from water to air, strikes the boundary, calculate the critical angle. So if this is a critical angle, this is how my light would be going. Critical angle, R is 90. So using sine C, N2 over N1. Second medium is air, first is water, using calculator. Then my answer is around 48.8 degrees. So I'm going to write C as 48.8 degrees. Now total internal reflection. But what happens? Let's go back to this diagram. Fine, I'm increasing my angle, I'm increasing my I, my R increases, and one point in time when I is critical angle, R becomes 90 degree. But then what happens if I further increase my angle? What would then happen? I'm going to just copy that diagram to this page. Okay, so now if I increase the angle other than critical angle, so I'm now taking I as higher angle than critical angle. Okay, so let's just take I as angle greater than us. This is, now for this red incident light, my angle is greater than critical angle, so the light would come back into that same medium. So if I is greater than C, no refraction. All the light comes back into the same medium. And that is called total internal reflection. Okay, now what's the condition for total internal reflection? First, I should be greater than C. If I is not greater than C, light will not come back to the same medium. So that's the first condition. So if I write here, my first condition, angle of incidence should be greater than critical angle. And then for what kind of process, what kind of mediums critical angle is defined, the light should travel from denser to less denser medium. If that does not happen, the critical angle will not be defined. And if critical angle is not defined, how can you have I greater than C? So that's your total internal reflection. So if angle of incidence is greater than critical angle, all the light comes back into the same medium. Now this has a typical use. It is used in the optical fibers. What is optical fiber? It's the kind of fiber that is used for your internet cable. Okay, so if you have an internet cable at home, it is something made up of something called as optical fiber. Now what is optical fiber? It is kind of like a fiber that is made up of high quality glass or plastic. So this is a high quality glass or plastic cable, and then what it has is, this is very, very high refractive index, and then what it has around it, this is called core, and then around it you have, this cable has a cladding, and that cladding, this cladding here has a less refractive index. So I'm just going to make the diagram here again. So this is my core, which has high refractive index, and then it has around it a cladding which has low refractive index. Now what happens is the light ray that is entering into the core in a form of your data signal, electromagnetic wave, it could be your the light wave in the form of carrying communication, or let's see, okay, we're using it for high-speed data transmission. So what happens is, for a long distances, this data could be lost if we're not using total internal reflection. So if you want this light to be inside the light, inside the fiber, then this entire light has to undergo total internal reflection. What I mean by, see, the light ray is entering at this part of the fiber, and hundreds of kilometers away, this signal, which is a internet signal, let's say, and you want to receive it hundreds of kilometers away in your house, and you want the signal to be strong. Now imagine the signal which is hitting here at this part, a part of it is lost and a part of it comes back inside. Then it hits here, a part of it is lost, and then part of it comes back inside. So if every point it hits this boundary, a little bit of signal is lost, you're going to have a very, very weak internet. So then what is done is, it is specifically designed refractive indexes, this is N2 and this is N1, so that when light ray enters into this optical fiber, there's this part goes missing. Okay, there is no loss of the signal because of the total internal reflection. So I'm going to remake the diagram. So if this is, say, whatever light ray hits this point, all of the light is reflected internally. That means what angle this should be incident at. If you want all the light to come back inside, this angle here should be greater than the critical angle, say, and then it goes here again and comes out. So at every point it hits the boundary, none of the light goes out, no light is lost, no signal is lost. So whatever light enters the optical fiber, it is received at the other end. Condition, I should be greater than the critical angle. What should be the critical angle for this? It should be defined by something as this N2 over N1, where N2 is the refractive index of cladding, the outer part of your optical fiber, and N1 is the refractive index of your optical fiber, which is generally glass or a plastic, whatever it is. Okay, this is the refractive index of the core. Okay, some of the exam questions kind of like these. So if the concept is clear and you go and solve your actual exam questions, it would not be difficult. You'll be very surprised to see these kind of questions in your exam questions. What are the conditions required for total internal reflection? What is the condition? First condition, angle of incidence is greater than critical angle. Please don't write in short form, write the full form. Second, it should travel from denser to a less dense medium. Okay, dense to less dense medium. That's the condition. How optical fibers use total internal, so this is total internal reflection, to transmit light signals. How do they use the process of TIR? So what is happening is, there's multiple reflection happening at different points in the optical fiber, and because of this multiple reflection, and there should be total internal reflection at each point only if the angles exceed the critical angle. If the angles does not exceed the critical angle, there would not be any TIR. So let's start. First point, light continuously gets reflected inside the core. Okay, so let's just write the first point, continuous reflections at different points in the optical fibers. Okay, just making a diagram to aid your understanding. So this is your optical fiber core and then the cladding outside. So multiple reflections. So these are multiple reflections happening. Now the core has high refractive index, and as compared to what? As compared to the cladding. Okay, otherwise if it is not high, it will not go from a denser to a less denser medium, and if it is not going from a denser to less denser medium, there will not be any critical angle. And if there's no critical angle, your angle of incidence cannot be greater than the critical angle, and there will be no TIR. So if angle of incidence is greater than critical angle, continuous. Now you started with reflection, now you say continuous total internal reflection takes place with minimum loss of energy. There will be always a loss of energy. You cannot make it zero. No process can ever be 100% efficient with minimum loss of energy. All right, let's try another one. Oh, here you go. You can read the answer. Okay, all right. Next one. A glass prism has a refractive index 1.6. So it has a refractive index of 1.6. A glass prism. So a prism is generally in the form of a triangle. So I'm just going to make it a triangle here. A ray enters normally. So it enters normally and strikes the internal face. So it strikes the internal face at, so this angle is 50 degrees. Determine whether total internal reflections occurs or not. So now from this face, this is your now N1, this would be N2, because it will go from denser glass to rarer air. Say my critical angle for this would be using this N2 over N1. N2 is now is 1 because it's going into air. So 1 and N1 is 1.6. Say using calculator, it gives me angle around, so critical angle comes out 38.7 degrees. So it is incident at 50 degrees, but the critical angle for this surface is 38.7. So because my incidence is greater than critical, TIR occurs, total internal reflection occurs. Yes, so that's your answer. That's what it's asking, whether it occurs or not. Now the common mistake would be to use N1 as air and N2 as glass. Do not make that mistake. Even if you do not know what is N2, what is N1, you should always know that in this is the trick. The numerator will be always less than the denominator. If your numerator is greater than the denominator, the sign function is not defined. You put in your calculator, you will give your wrong answer. It will say not defined. So always understand that this should be less and this should be more. So if it comes to that you're not getting it, then at least remember this. Let's try this one. A light ray travels from one medium to another, 1.8 to 1.2. Calculate the critical angle. So it travels from dense to less dense. So this one is N2 and this one is N1. So critical angle is now N2 over N1, which is 1.2 divided by 1.8. Using my calculator, then critical angle comes out to be around 41.7 41.8. So critical angle is 41.8 degree. So if angle of incidence is 30 degrees, which is less than critical angle, light goes into medium B. Okay, light refracts. Of course, then there's no internal refraction happening, then it will go into the same next medium, just like it as expected. So light refracts into medium B. Okay, that's it. So what we learned something new is that if there is refraction happening and light is traveling from dense to less dense medium, the angle of incidence can become critical angle. The condition for critical angle is that angle of refraction should be 90. If angle of incidence is greater than critical angle, all the light comes back into the same medium, and that process is called total internal reflection. All right, well done. See you again. Thank you so much. Bye bye.